Nat 4-5 Physics, Weight and Mass. The key areas we will look at today are the definitions of weight and mass, the relationship between weight and mass, gravitational field strength, and calculating weight, mass, and gravitational field strength. Weight and mass. Weight is a force. The weight of an object always acts downwards, and we know we always have to specify a direction for a force because force is a vector. Weight is measured in newtons, and the weight of an object can change. Mass measures how much matter there is in an object, so the amount of stuff that it's made of. Mass is measured in kilograms, and the mass of an object stays the same at all places. The weight-to-mass ratio is usually called gravity, and gravity is the short way to write gravitational field strength. Gravitational field strength is measured in newtons per kilogram. From practical work or research, you could find the gravitational field strength value for planet Earth. You would want to measure the weight of an object and measure the mass of an object. So you could use a Newton balance to find the object's weight, and you could use some scales to find its mass. Here is a possible set of data from the practical work that you could be doing. So we've got lots of different objects there. We've got a mass carrier, a tripod stand, Newton balance, all the way down to a whole pupil. We can have a look at the weight, we can have a look at the mass for each of these objects, and if we actually take the weight and divide it by the mass, you can see that we have some very similar numbers just here. So we've got 8.8, 10.9, 9.0, 10, 9.5, 10.3. They're all very, very similar, and they actually are very close to a constant value. And this constant value is what we call the gravitational field strength on Earth. So this weight to mass ratio is known as the gravitational field strength. Gravitational field strength is defined as the weight per unit mass, and for planet Earth, this is 9.8 newtons per kilogram. This means that there is a downwards force of 9.8 newtons acting per 1 kilogram of mass. Gravitational field strength can vary depending on where you are on the surface of Earth. Altitude and latitude make a big difference. Altitude being how far you are away from sea level, so if you're up a mountain, and latitude is where you are on Earth, so at the equator or up at the North Pole. What you could do is you could try and find out where the gravitational field strength is greatest and least on the surface of Earth. Weight can be calculated by using this equation, W equals mg, where W is the weight measured in newtons, m is mass measured in kilograms, and g is gravitational field strength measured in newtons per kilogram. This equation can also be written as a triangle. You can use the little phrase, "Where's my glasses?" to help you remember this. Example 1. Stefan, with a mass of 50 kilograms, visits Mars, which has a gravitational field strength of 4 newtons per kilogram. A, state his mass on Mars, and B, calculate his weight on Mars. We can see that for part A, state his mass on Mars, a state question does not require us to use an equation. So you need to notice that mass does not change dependent on what planet you're on. And so if Stefan's mass is already 50 kilograms, his mass on Mars is also going to be 50 kilograms. For part B, the question says calculate, so we know we're going to have to use an equation, and we have to calculate weight. So having a look at the question, we have a mass, we have a gravitational field strength, and we want to calculate a weight. So we want to use the equation W equals mg. Our weight has a question mark. The mass is 50 kilograms, we already knew that one. And the gravitational field strength in the question is 4 newtons per kilogram. So using W equals mg, we need to plug in our numbers. So W equals 50 multiplied by 4, which gives us a final answer of 200 newtons. Example 2. Ross wins a trip to the moon, which has a gravitational field strength of 1.6 newtons per kilogram. His weight on the moon is 72 newtons. Part A, calculate his mass on the moon, and part B, state his mass on Earth. Part A, we can see says calculate, so just like before, we want to write down W, M, and G. You can see in the question we have the gravitational field strength and the weight, and we want to calculate the mass. So W equals 72 newtons, M is our question mark, and G is 1.6 newtons per kilogram. W equals mg, so 72 is equal to m times 1.6. M equals 72 divided by 1.6, which is equal to 45 kilograms. And part B is state Ross's mass on Earth, and we know that mass stays the same no matter what planet you're on, so again his mass is going to be 45 kilograms. Example 3. Sally takes a trip to space but crash lands her spaceship. Sally's mass on Earth is 65 kilograms and her weight when she crashes is 715 newtons. Determine on which planet she crashes. So here we've actually been given a mass and we've been given a weight. We need to find out the gravitational field strength of the planet she crashes on and then use the data sheets to figure out what planet it is. So W equals 715 newtons, M is 65 kilograms, and G is our question mark. We want to work out what G is. W equals mg, so 715 equals 65 times by our gravitational field strength. So G is going to be equal to 715 divided by 65, which gives us an answer of 11. And remember, that's newtons per kilogram. Here is our data sheet. You can see we've got lots of different numbers down there for the gravitational field strength on the surface of various planets. We are looking for the number 11. And you can see about halfway down there, we can see the number 11. That is Neptune. So our final answer is Neptune. What you could do for some extra practice is copy and complete this following table. Pause now to give yourself enough time. Now you can check your answers.